Hi, my name is Madison Matthews, and this is my Physics 2211 Lab 2 report on projectile motion. So the purpose of this lab was to demonstrate and understand how objects move in projectile motion, and we did so by comparing experimental projectile motion data with two different computational models of projectile motion, one that included drag and one that included no drag and only gravity. And we did this using GlowScript for our code, Tracker to track our experimental object, a computer to run the code, a camera to record our object moving, and then a balled up sheet of paper to act as our projectile. So the fundamental physics concepts used here are the momentum principle, which means that the net force is going to be change in momentum over change in time. Then we also used the position update formula, the velocity update formula, the force of gravity, which is mass times the gravitational constant 9.81, and the force of drag, which is the drag constant times velocity squared. So for this experiment, the first part was getting our experimental data, and we did so by recording a video of a paper ball moving in projectile motion with the camera, where the system was the paper ball and the surroundings is everything else. Then we tracked the object in Tracker to graph the paper's motion over time. Then the second part of the experiment, we created a computational model in GlowScript for the paper's motion over time with gravity as the only force, not including drag, and then we recreated the computational model with gravity and drag included. And finally, we compared the two computational models to the experimental model that we received from our data in Tracker. So this is the video of the paper ball in motion. Oop. And these are the graphs we received from Tracker after analyzing that video. So on the left, we have the X position with respect to time, and you can see that it's moving in relatively straight line, like increasing because the ball is moving from one side of the screen, the left side to the right side. And then on the rightmost graph, you can see the change in position of the Y with respect to time, and you can see that it's moving in the same shape as the paper ball did because it's going up and then back down. Next, we created a computational model with only gravity in GlowScript. So as you can see, we inputted the mass of the ball, and then we also put in the initial conditions, so the position and the velocity vectors. And then we changed our delta t to do the time of each time step based on our Tracker video. And then for this model, we set b equal to 0 because there's no drag force. And then on the second part of code over there where we put the calculation loop, you can see we put in our vector for gravity, and then also our fnet vector we just set equal to gravity because that's the only force. And then for this computational model. And then you can see on the right we have the position with respect to time and then also the velocity. Then for the second computational model, we changed it up by estimating the drag constant. And then also in our calculation of the net force in the calculation loop, we had it so that there was actually drag being considered. And you can see how this changed the position graph and the velocity graphs on the right. So here is the experimental and computational data all in one graph. So the one on the left is the X position, and the one on the right is the Y position. Possible sources of error for this include tracking errors when we actually tracked our experimental data, because you have to manually click the center point. So that could be a reason why the graphs don't exactly match up. Then also we did have to estimate the B value for the drag force, and we also had to estimate the mass of the paper ball because we just looked up the mass of paper. We didn't actually use like a scale to measure it. So a few what if questions. The first one, do any of our models predict a terminal velocity? Terminal velocity happens when drag force equals the force of gravity, and so the net force is 0 and the object, in this case the ball, will have no acceleration. So the first graph does not have a terminal velocity, but the second one will eventually reach terminal velocity as it approaches the asymptote, because you can see the velocity is slowly approaching like 3 at the bottom. Then the second what if question, if the object were thrown straight up with the same initial speed, how would that compare to like how long it would take to reach the ground in projectile motion? So the object thrown straight up will take a longer time to reach the ground than in projectile motion with the same initial speed, and that's because it has more initial velocity in the vertical direction, so it'll reach a higher height and then it will take longer to eventually come back to the ground. So thank you.